TechTalk is a series of forums and dialogues given by engineering researchers of diverse academic background to share the insights on innovation-related topics. So today we are very honored to have Professor Vincent LAU give a talk, and the title of his talk is Integration of AI and Wireless Networks for 6G Systems. Professor LAU is Chair Professor of the Department of Electronic and Computer Engineering and Director and Founder of the Hong Kong UST-Huawei Joint Lab at Hong Kong University of Science and Technology. Professor LAU obtained B.Eng from Hong Kong U. He's one of our distinguished alumni. And a PhD from Cambridge University. He joined Bell Labs and then the Department of ECE at Hong Kong UST. And currently he's Chair Professor and Director of Huawei Hong Kong UST Joint Innovation Lab. He is a Fellow of the Hong Kong Academy of Engineering Sciences, the IEEE, the Hong Kong IE, the Culture Senior Research Fellow, and Changjiang Chair Professor. He has published over 400 papers and many US patents. His current research focus includes stochastic optimization and analysis for wireless systems, massive MIMO systems, sparse recovery, Bayesian machine learning, mission critical IoT, as well as physical layer caching for wireless networks. So without further ado, let us welcome Professor LAU.
Thank you. Thank you, Victor, for the kind introduction, and it's a great honor for me to be here. Especially, I spent my 3 years undergraduate in Hong Kong U, and when I walked to the new campus, I found that I can still find a lot of beautiful memories. And thank you very much for coming to this talk despite the rainy weather. And it's very nice to meet friends and colleagues around. And then, so today I'm going to talk about the integration of AI and 6G wireless communication. So I will explain what do we mean by the integration. Okay, thank you. Yeah, so first, take a look at the mode of machine learning. So today, I guess we are mostly using this machine learning in this centralized mode, meaning that the model and the data set coexist in the cloud like this. So we know machine learning requires training, and training requires lots of data. So these data and the model, they finish the training all in the cloud, and then when you use it in the cloud as well. So this is the current machine learning. But then we know that in the near future, the paradigm of machine learning or AI will be shifting from this centralized machine learning to all the way to what we call federated learning. So the scenario is like the data set naturally exists not usually in the centralized manner, but the data set usually exists in a distributed manner across all the devices. Maybe your mobile phone will naturally collect a lot of photos, images, and whatever. You have cars, you have laptop, all these kind of devices naturally will have a lot of local data set. So therefore, the scenario would be the model may be in the cloud, but the data set will be distributed across multiple devices. So how are we going to train the neural network when this is the scenario? So of course, one way to do this is we have a totally so-called distributed on-site learning, in the sense that each device download a model and then use the local data set to train the model. Now, obviously, this is not very good because usually the local data set is not too big in size, right? And we know that the machine learning performance depends very much on the size of the data set. So therefore, in the future, something called federated learning was created to overcome this problem. The problem is yes, the data set exists in the local devices. But then we want to, when we train the neural network should be able to benefit from this distributed data set, right? So that means when you train the neural network, the model, you want to utilize all these distributed data set available across devices, okay? Now, so when this is the scenario, so how is wireless communication related to AI? So we can see that how do you, when you want to utilize this data set distributed across multiple devices, and namely lots of devices, then you will need to find ways to communicate the model and the data, right, across these devices. So you can see that in the training of the neural network, in the future scenario, the wireless network will be sitting in between the data set and the model. So therefore, wireless network will play a very important role in the facilitation of the future AI application. Now this is once again another illustration of the future scenario, so-called federated learning. So you see you have lots of devices which accumulates lots of local data, and then you want to utilize all these distributed data set to train a global model, right? So you can see that if these devices are linked to the global model through a wireless network, then the wireless network will be sitting in between the data and the model. Now, so if the wireless network, now like today's wireless network, it has been the philosophy when we design communication network. The goal of communication network is just to set up a transparent data pipe between point A and point B. It doesn't care what's the application behind this data pipe. That's the segregation of application. So that it has been the philosophy, even up to today's 5G network. Okay, so, but as we'll talk about in the later part of this talk, since AI is a very important application, and when you design wireless network with the mind that the application is going to be AI, you can actually have lots of room for optimizing the wireless network if you are application specific. So we will see what we mean by this. Okay, so now, in transition from the centralized machine learning to the future federated machine learning, there are quite a lot of technical challenges we need to overcome, right? So as I said, right, so if you have a centralized training and inferencing at the cloud in a current manner, you will have heavy computational overhead. So when you train the neural network, when you use the neural network after training, you will involve heavy computational overhead, and that data set naturally exists in the devices, right? So if you're talking about distributed training and inferencing at the devices, then you have limited data set because you will only be able to utilize your local data set, which will severely affect the performance of the neural network. Now, in the future collaborative or federated training and inferencing between devices, then you have to leverage on the distributed data set available across multiple of devices. But then on the other hand, you want to avoid sending raw data to the cloud. Like the raw data can be your picture, can be your video or things like that, because obviously you may be concerned about privacy, right? You probably won't like to send your picture directly to the cloud for training a certain neural network. Now, as I said, you have wireless network in the loop, in the training loop between the data set and the cloud and the model. So if you just use a naive way to send the data to the cloud to train the neural network, then you will have huge communication bottleneck. Don't forget that the model we're talking about, the neural network model, usually we are talking about billions of weights. We are talking about this order of magnitude. So you might imagine you have to send huge amount of data set to train a neural network with billions of weights. Then it is not something very easy. So we need all this, if we have to really support this collaborative training and inferencing in the future scenario, we need to find ways to better facilitate such a future collaborative training environment. Okay, so now in this talk, when I say integrated AI and wireless, there are actually two meanings behind this. The first meaning is wireless communication for efficient AI application. That is to say, if we know that AI would be a very important future application, can we take this into account when we design the future wireless network so that we can have more efficient communication supporting AI application, okay? So that is one side of the picture. Okay, so specifically, there are many possibilities. But then, and in this talk, I won't be able to go through all the details for this, but I just want to highlight the possibilities. So the first thing is, when we talk about more efficient communication network, one thing that is very important is the multiple access. So what do we mean by multiple access? Imagine I'm the cloud, right? And you guys are the devices. You guys own the data set, but you want to send something to the cloud. So this is a multiple access, many-to-one communication topology. So how do we do efficient multiple access, right? So that is one important topic, especially we are talking about many devices, massive number of devices in the future, okay? Now, another important consideration is what we call green AI, is the communication efficient federated learning. That is, the communication network is sitting in between the data set and the model, right? So how do we improve the communication efficiency? So we'll have an example to illustrate what we mean by this. The third item is what we call structure model compression for computational friendly AI. What do we mean by computational friendly AI? So far, we have been focusing on training, right? The training of the neural network. But even if you are finished the training, just want to use the neural network, just the inferencing itself can be computationally intensive. Right? We heard about a lot of this, new design like the AI chips, GPU, all this. All these are used to facilitate efficient computation just for the inferencing, right? So this is also something that is very important. And finally, when we talk about training, right? So you need to, you can think of the training as a stochastic optimization problem. You want to minimize some objective function with respect to some variable. The variable will be the model weights, right? So traditionally, I mean, even now, most of the algorithms that we use in training the neural network are derived from something called stochastic gradient. Now, stochastic gradient is nice because under very mild condition, it can converge. It's pretty robust. But the problem of stochastic gradient is it is very slow. That means you need to go through many, many iterations before you can converge. So in this part of the work, we are trying to see, can we accelerate the algorithm? Can we design better algorithms that can converge faster, much faster? Okay, so these are the four focus areas when we talk about designing better wireless network for supporting AI. Now let's look at the multiple access for now. Okay, so now let's have a quick review of the traditional way of doing multiple access, right? So traditional way of multiple access. Now multiple access plays a very important role in many systems like LTE, like 5G, like Wi-Fi, for example. Now, but there are different ways to do multiple access, right? One way is, for example, if you look at Wi-Fi, it's called contention resolution. So what does that mean is Wi-Fi is like a completely decentralized entity, right? So imagine you guys, I'm an access point. You guys are the Wi-Fi devices, right? And let's say you guys want to talk to me, okay? But how do you do it? So this is carrier sense multiple access for Wi-Fi. The protocol, the spirit of the protocol is like listen before talk. Now, there is no centralized body to tell you when to transmit, okay? You guys determine on your own when can you transmit the packet. But the constraint is if there is more than one person talking at the same time, this is called collision. And collision is bad. When there is collision, I won't be able to hear anything, right? So how do you do it? So everybody, just when you want, before you transmit, you need to make sure that there is nobody talking, right? Common sense, right? So that's why this is based on listen before talk. You listen to the media, make sure nobody is talking. And then there are some more sophisticated mechanisms, but essentially, you want to make sure when you transmit, nobody is talking, okay? So the reason is for this is collision. When there is more than one person talking at the same time in the same channel, is something bad. When there is collision, the receiver won't be able to hear anything, okay? So that's the principle of contention resolution. Essentially, everyone transmit on your own, but if there is collision, then we handle the collision afterwards. That's one philosophy of designing multiple access in a decentralized manner. Another philosophy is something we call collision avoidance. This is like 5G, for example. Now, same scenario, you guys are the mobile devices. I'm the base station. If you want to talk to me, right, this is also a multiple access direction. You cannot just talk anytime you like. You need to raise your hand. by sending a so-called bandwidth request. You need to use some mechanism to send a bandwidth request to the base station. And then when I receive your bandwidth request, then I will send in a downlink direction an assignment message. I will allocate this particular resource block and allocate for you so that you can transmit on this allocated resource block, right? So there's some handshaking, so-called scheduling in the process. So that means whenever you want to transmit something, you cannot transmit immediately. You need to go through some handshaking procedure, and that incur delay and latency, right? You need to wait until I tell you where to transmit before you can transmit. Now, in either of this, so this philosophy is to avoid collision, right? So when I allocate this resource block to you, only you can transmit at that moment of time. So nobody else will transmit, so there is no collision. So in either of this philosophy, namely collision resolution or collision avoidance, the common philosophy is interference, or so-called collision, is bad. It's something bad we need to avoid, okay? Because of that, so if you look at either of these, they are not scalable when we have a large number of sensors. For example, contention resolution in Wi-Fi. When you have many, many Wi-Fi devices going through this same CSMA protocol, the throughput will drop because the bottleneck will be collision in that case. In other words, the other scenario, if you're using the LTE or 5G, the 3GPP method, if you only have a resource block, common resource block for serving all these users, then you need to wait for a very long time in the order of the number of devices. You need to wait for a very long time before you can transmit your packet, okay? So either of this, there will be heavy penalty. It's not scalable with respect to a large number of devices. So, okay, so how is it different when we talk about AI? Now, when we talk about AI, now, all this previous philosophy I explained just now is based on an assumption that interference or collision is something bad. When there is more than one user talking at the same time, it is something disastrous we should avoid, okay? This is based on an assumption that if we have, let's say, K devices, the goal in the traditional communication sense, the goal of the receiver is to separately decode what could have been transmitted by all these K users separately. That means the goal of communication in the conventional sense is the receiver needs to estimate U1, U2 up to UK, the symbol transmitted by this K device respectively, okay? But if we look at the application together in a holistic way, like this is used to train the neural network in the cloud, for example. So after we estimate U1, U2 up to UK transmitted by these sensors, let's say these sensors or these devices are transmitting gradients or stochastic gradient. The goal is to train the neural network, right? So at the neural network, what do we need to compute at the end? Is to compute the sum of all these stochastic gradient together so that you can use this sum of the stochastic gradient to do the update, to do the stochastic gradient, model weight update. So the goal is not to estimate the individual data. The goal is to estimate the sum of the transmitted data. Now, this is very unique because this is, in your normal circumstances, this will not be the case. But in training the AI, this is the situation. I don't need to know the individual mini batch gradient. What I need to know is the sum of this gradient. Now, if you look at the conventional way of communication rely on multiple access scheme, either contention resolution or contention avoidance, collision avoidance. The goal is to let the receiver receive U1 hat, U2 hat, up to UK hat. And then, but after the receiver obtain this, what the receiver has to do? Receiver has to sum them together to get what they want and proceed further to train the network. In other words, the communication and the computation are separated. The communication and multiple access algorithm or protocol is to engage or ensure you have a proper communication so that the receiver knows about what could have been transmitted by these K devices. And then the computation will be internal to the server side. Right? After you receive all this U1 hat, U2 hat, up to UK hat, you compute, sum them together, and then do whatever you like. Okay? That's the conventional way of communication plus computation. But now if you look at this in a holistic way, the computation required that is a summation naturally exists in the communication channel. Imagine if all these devices synchronize in time in a resource block, transmit the gradient together. if they transmit simultaneously on the same channel, what you receive is naturally the summation of whatever transmitted. And what you need is just a summation, right? So there is no need for you to first individually detect the individual symbols. Okay? What you care at the end in a holistic way is just you want to estimate the sum. So if that's the case, why we need to separate the communication from the computation? We can integrate together because the channel, the wireless channel, naturally is doing the computation for you. Okay? So this way, you can think of that as an integrated communication and computation. And this is what we call over-the-air aggregation. Over-the-air aggregation. So unlike the traditional multiple access philosophy, where collation is bad, in this context of training a neural network, collation is actually something good because what we want at the end is the summation, is the estimated summation rather than individual components. Now, utilizing this unique feature, the multiple access scheme can be redesigned. The previous traditional multiple access is to avoid collation, okay, separate collation. But now realizing this end-to-end goal is just to compute the sum. The new multiple access mechanism should encourage collation. So try to align the collation as much as possible. Because in this way, you maximize the efficiency of the communication resource. And because of that, you have lots of advantage. For example, you just need a constant radio resource block to support a large number of users. In a conventional multiple access, if you have large number of users, you have a corresponding penalty in the latency, right? But now, because we don't need to separate collation anymore, so with even one resource block, we can support arbitrary number of users with no delay, zero access latency. Okay, so zero map latency. And this is very important for very real-time applications requirements. Okay, so that is one opportunity that I said, when you design a wireless network, if you have an application in mind, and you take a holistic picture, what do you need in the application? Then in this case, you can have a much more efficient communication network. So the multiple access is one example, all right? Now, another example I want to share with you is data-aware sensor scheduling. So sensor scheduling is like, okay, you have, like I'm also the server, and you guys are the sensors or devices. Because of limited communication resource, you may not want all sensors to transmit simultaneously, right? Because everyone have power constraint and whatever. So you need to schedule at any time. You want to determine which sensors should transmit and which should not. Okay, so this is called sensor scheduling problem. Now, conventionally, the sensor scheduling problem has been well studied. Okay, so traditional way of doing sensor scheduling in wireless network is now each sensor, between the sensor and the communication and the server, there is a so-called fading channel. So that means the communication link may not be always good. Sometimes this sensor may not be having a very favorable channel to talk to the base station, but the other sensors will have a very good communication channel state to talk to the base station. Then in that case, the conventional wisdom is saying that, okay, those sensors with good channel condition should have higher priority compared to that other sensors that doesn't have the good channel condition, because the one with better channel condition can utilize this radio resource block more efficiently, right? Sustain higher throughput, okay? So this is the traditional wisdom of doing channel-aware scheduling. Now, in AI, if the sensors are trying to send data or send gradient to the server to train the AI model, so how is it different? Now, when we have this holistic picture in mind, once again, the data that each sensor is going to send may not have the same importance, right? For example, this sensor may be carrying a very important training data, which when this data is sent to the server will be able to make a big adjustment to the weight, right? But the other sensors may carry some data which doesn't matter too much, even if the sensor is not sent. Even if the sensor is sent that kind of data, less important data, the model weight is not going to be affected a lot, right? So because of that, naturally, you also want to give the sensor with more important data, okay, higher priority. Now the problem is, so you have two philosophies. One is data-aware scheduling. Those sensors with more important data should have higher priority. The other philosophy is the sensors with better channel condition should deserve higher priority, right? So, but then at the end, how do you merge these two together? At the end, you can only have a linear priority across all sensors. So that is the difficulty. Okay, so now existing, as I said, existing channel aware only. So if you only focus on channel aware, channels condition, then you have ignored the data importance, right? So you have ignored the data importance. That is not good. There are also some existing schemes that only take into account of data aware scheduling. That is, you ignore the channel condition, ignore the fact that different sensors have different channel condition to talk to the base station. Now, if that's the case, you will create something called bias. Now, what do we mean by bias? Now, imagine you run a company, okay? So data aware scheduling means that you give the sensors having more important data the more opportunity to send compared to the sensors with less important data. They will have less opportunity to transmit, right? So, and I said that if you do it this way, you will create a bias. Now, what do we mean by bias? Now, imagine you run a company. You are the boss, right? And your sensors are your subordinate. If your subordinate always filter the message before they talk to you, they only report the good things and shield away from the bad things, right? So if you're the manager, what do you get? You only get a distorted picture of the company, right? So it's like people saying, 報喜不報憂, right? So imagine you run a company this way, you will be making wrong decision all the way, right? Because you have a distorted picture. So obviously, it's the same situation. When the sensor priority is based on the data importance, the distribution of the data that the server will obtain will be distorted from the true distribution. So therefore, when you train the neural network this way, you will have bias. So this is like the bias. So this is the loss function. The lower, the better. And then this is like data aware scheduling only, right? So you can see that after you go through many iterations, 6,000 iterations in this toy example, you see that you suffer a large gap. And this gap is due to the bias, so-called data distortion. Okay, so the challenge is we know that we need to make use of both the channel and the data importance when we do sensor scheduling. But how do you do it? And you don't want to have bias as well. So the way you do it is like, so when sensors transmit, traditionally, sensors just transmit the instantaneous gradient to the server. But now, in order to remove the bias, the sensor should not just transmit instantaneous gradient, but you also have to add the so-called accumulated residual. This accumulated residual accumulate the past gradient, which you haven't got a chance to send it to the server. So for those so-called gradient that you don't have the chance to send it the data, you put this locally to the so-called residual to keep track of the unsent, untransmitted gradient. Now in this way, when you get a chance to send, you send the instantaneous gradient together with the accumulated residual. In this way, you create, you have the opportunity to correct for the bias, okay? And then, so now at the end, how do you schedule the sensor? How do you schedule the sensor to take into account of both the channel condition and the data importance? Well, for that, you need some sophisticated math, which I'm not going to go into details, but you need to formulate an optimization problem so that the optimization objective has to be something that is related to the convergence of the training algorithm. Okay, so here we use something called near-Prof drift, and the near-Prof drift will be something related to the convergence of the training algorithm. And then the optimization variable would be the sensor scheduling variable, which sensor should be transmitted. Okay, so by solving this problem, we got some nice result. So this is a proposed solution. And then you see that the proposed solution would be very close to the benchmarking solution, which is like all sensors transmit, right? So the black benchmark is an expensive solution, but the red proposed scheme is a low-cost solution. In cost refers to communication resource. We see that they achieve similar performance, right? But compared to the other baseline, they have suffered from this kind of what we call data distortion gap. So this is another example of when you design scheduling algorithm in a communication network. If you design with the holistic goal of that this is going to train the neural network, you will end up having a much more efficient design. Now, the third example that I mentioned at the beginning is, okay, so after we finish the training, say we are going to use the neural network, trained neural network to do computation. Okay, so but computation is very expensive because the neural network we're talking about have billions of weights around. So even if you just want to compute the output for a given input, it's going to be very expensive. So how do we deal with this computational problem? So like what I said, is heavy computational overhead during the inferencing as well as the training, right? And heavy communication overhead as well. Now, so this is a simplified picture. So traditional method of doing this kind of so-called model compression is, we found that after you train a neural network, let's imagine you have billions of weights around this neural network. You can imagine not all the weights are of equal importance. Some weights are very small, okay, compared to the others. So the pruning is like, okay, so since this weight, for example, is only having very small weight, how about I remove it? If I remove it, it shouldn't have big influence to the overall performance, right? So this is the idea. You prune the connection, you prune the neurons according to the weight. So there are different ways of doing this pruning, but unfortunately, this kind of pruning is very heuristic. And since after you prune sufficient number of weights, for example, you are starting with, let's say, 1 million of weights, and let's say you prune away 50%. Now, although each way having a small contribution, but if you prune away 50%, the accumulated errors can be pretty big, right? You never know. So this kind of trial and error method depends on your luck, right? Sometimes it works, sometimes it doesn't. So a more systematic way of doing this kind of pruning is, can you take into account of this kind of structure constraint? You want the model weight represented as a model weight matrix, okay? You want the matrix after you finish the training. You want that matrix having some structure, what we call structure, and that structure will be computationally friendly. That's what you want to do. You want to embrace this structure constraint at the beginning of training, okay, in the formulation of the training. Now, what do we mean by structure? What is a good structure and what is not a good structure? So for example, one thing is, okay, let's say I want to prune away 50% of the weight. That means I just want to have 50% of surviving weight after finishing the training. Now, if I don't have any additional constraint, so this 50% of surviving weight can be anywhere on the matrix, right? So this is called random data path, totally random data path, random sparsity. Now, this empty position means the zero weight, having zero weight. This will translate to some missing edge in the overall neural network data path, okay? Now, unfortunately, this is not so desirable, okay? Because yes, although you prune away 50% of the weights in this way, but this kind of result may not translate directly if you work on the AI chipset design or work on VLSI data path and control path. You'll know if you only have a 50% sparsity model weights like this, it won't translate automatically to 50% saving in computational overhead. For some reason I'm going to explain. So because of that, you want to encourage more structure sparsity, meaning that, yes, I want to have 50% of the weights being pruned away, but I want this surviving weights to be organized in a more structured way so that this surviving matrix could be translated to a more friendly data path and control path in the actual ASIC implementation, okay? So the key message to take away is 50% weight pruning doesn't translate to 50%, doesn't always translate to 50% of computational saving, okay, in the actual data path design. So now a better way to create structure or encourage structure is like, again, let's say 50% of surviving weight, but we want the surviving entry to be organized in a better way. So one way is, okay, you want to make sure that the surviving weights will be clustered in a row so that some row will be totally empty. Now, this row in a weight matrix will be translated to a neuron in the actual data path. So if we have the whole row being empty, that means this neuron can be deleted in the data path, all right? So this sounds nice, right? Because like here, none of this row is empty. So that means all the neuron must be survived. It's only the edge connecting the neuron that are pruned away. So this will not be very beneficial in the computational saving, okay? But if you prune away a neuron, that's a different story, right? So the whole neuron needs to be, can be deleted. That's one way better. But still, you look at this surviving structure. These surviving neurons are still randomly connected to the next layer, okay? So in this way, the computation, for example, just think about parallel computation. all this computation are coupled together through this edge connection. So the computation is still full of coupling. So this is also, this kind of so-called structure weight is better than this, but still, you have rooms for further improvement. So what is the desired structure? The desired structure will be something like this. Okay, so you want to cluster these surviving weights together so that you leave more rooms for empty rows, because empty rows means empty neurons, right? You can delete the neurons. You also want these columns to be clustered together, because this column clustered together means these connections are also clustered together, minimize the cross-coupling. Now, if you have a data path like this, then you imagine you are trying to map this into the ASIC data path implementation. You can see that you can have a lot of parallel computation. For example, computing this part can be decoupled from computing this part. So you can have a lot of parallel computation in your data path opportunity. So this is a more desired so-called structure weight. We want to put this constraint directly into the training formulation so that after we go through the training, the result naturally have this kind of desired structure, okay? So instead of doing this kind of heuristic pruning, after you finish the training, you prune away, take away those weights by hand, you want to do this systematically in the formulation stage. Now, the question is, now, as I said, there are highly desirable effect of having this structure. Now, you have high level of parallelism, okay? You have efficient neuron pruning, right? So you also have more efficient storage. Just imagine, let's say we prune away 50% of the weight. In the control path of the ASIC, if the surviving weights are randomly distributed all over the place, just to have a data structure to mark down the position of the surviving weights itself require very huge data set, very huge volume for that. But if the surviving weights are clustered together like this, then the representation of the surviving weights would be much more simplified. You just need to, for example, have an index to index the surviving cluster and another parameter to denote the size of the cluster. So in terms of the control path, in terms of the data structure, to just represent this kind of surviving weight is much more simple when the weights are clustered together. Okay, so we know that this is a desired structure. Now the question is, how do we enforce this in the training formulation? Now, again, some math here. Don't worry, I won't go into the details. So we adopt a so-called Bayesian approach. When we know, when I say training, it's like an optimization problem. So what is an optimization problem? We have an objective function. And every optimization problem has a few components. One is an objective function. What is the function you want to minimize, for example? Second is the variables. What are the things that you can control, right? And sometimes you may have constraints. So these are the three components. So traditional training is like you train a loss function. Maybe the loss function is what we usually call mean square error and plus some regularization, okay? And that is the objective function. And the variables will be the model weight, the weight matrix I just talked about. But instead of doing it in the traditional way, we take a Bayesian approach in the sense that the objective function we want to maximize, in this case, is what we call the posteriori distribution. And W is the model weight, D is the data set, okay? And the variables will be W, the model weight, and also some hyperparameters. Now, if you try to decompose this so-called posteriori distribution, it can be decomposed into the three terms, right? And in particular, the numerator, this term is called the likelihood. This likelihood term determines the relationship between the data set and the model weight, okay? So this is usually come with your observation model. This yellow part is what we call the prior distribution. This is the place where you can impose the structure, the structural properties that you want the weights to be. So, so in this work, we designed a three-level hidden Markov model to enforce the weights to have the desired structure that we just talked about. And then, of course, this is not that easy to solve, and then we have to use some other algorithm tricks, like variational Bayesian inferencing, these kind of techniques to get a low complexity solution. But skipping all these details, just to let you have an idea, this is an extension to federated learning, which let's skip this in the interest of time. So we can see that using this kind of Bayesian approach with this imposed structure, we get the better accuracy and with a much lower cost, much lower communication overhead. And then to give you an idea about, for example, the inferencing time, using the proposed structure with this cluster sparsity, we have inferencing time. We can finish the inferencing of this toy example, CIFAR10 dataset in 31.6 milliseconds. But if you look at the other state-of-the-art neural network architecture, you're talking about sometimes close to a double of the inferencing time. And this is the image on the surviving neurons. So the bright spots refers, so this is like a color map, a heat map. So dark region means the values of the weights are very small. The bright region means the value of the weights are very large. So you can see that after 40 iterations, the surviving weights basically clustered together in the same design structure that we want to have. So this is to illustrate this model. So this is an idea of we want to do model compression because not all weights are equally important. But instead of doing handpicked heuristic pruning, we want to put this structure as a constraint in the optimization formulation, in the training formulation. But what kind of structure is called desirable? So there is a huge gap between the surviving weights, percentage of surviving weight, and the actual computational saving in the actual ASIC data path. So the key message is you can have different ways of pruning the model weights. They all have 50% of the surviving weights, but they can have very different computational overhead in the data path and control path. Okay, so okay, now the fourth part, which I probably need to speed up, right? So how much time do I have? Probably not much, okay. Okay, sure. So I can do that. So the fourth part about designing a better wireless network, more communication efficient, this is closer to the training algorithm. So as I said, many of these, so the training of the neural network is actually a stochastic optimization problem. And many of these stochastic optimization problem, the solution to that is based on something called stochastic gradient. It's something based on stochastic gradient. So the stochastic gradient is like this. The model weight at t+1 is equal to the current model weight minus the step size times a gradient. So this is the basic form of stochastic gradient. Now, but the problem of stochastic gradient is it is slow in convergence. Although it's very robust, eventually it will converge under some mild condition. But usually it takes many iterations to converge, right? So you heard about if you want to train a very big AI model, it takes months of effort to train it, okay? That is related to the conversion speed, how fast it converges. Now, in the literature, there are different attempts to speed up these algorithms, to speed up the training algorithm. So a very famous attempt is called momentum. So instead of just updating the direction based on the steepest descent direction represented by the gradient, you also want to have another direction called momentum, okay? Now, there are different versions of momentum. In short, this momentum was shown to be able to speed up the convergence substantially in a deterministic problem. That is when this gradient doesn't have noise, when you have an exact gradient. These momentum methods are very efficient. For example, this is a convergence curve of the stochastic gradient, very slow. This is a curve of one way of momentum-based algorithm. You can see that substantial speed up. But once you put noise in the gradient, this advantage is gone. Okay, so these kind of momentum algorithm show great success in deterministic case, but they are very sensitive to noise. When you add noise to this gradient term, all this advantage vanish. In some versions, for example, this is called heavy ball. When you have no noise in the gradient, this is very good, right? But when you add noise to the gradient, this is even diverging. So what's going on here? Now, why we have noise in the gradient to start with? Now, to keep the story short, the noise in the gradient, when you have a communication network, wireless communication network in between the data set and the model in the cloud, when you have a wireless network in between, the noise in the gradient is coming from two effects. One is channel fading. When the sensor sends data to the server, you suffer from random channel fading. So that will give you a time-varying signal-to-noise ratio of the gradient. That's one effect. The other is the random mini-batch size. Different devices will have a different mini-batch window, and that will create different noise in the quality of the gradient. So these two effects will contribute to noise in the gradient in practice. Okay, so, and as we explained, the noise in gradient is very bad. Okay, so we need to design better algorithm, but the first thing is we have to understand why this momentum algorithm fails when we have noise, right? So using some conventional way of analyzing this algorithm is using discrete time approach. And discrete time approach, because of the barrier in the mathematics, it's very difficult to get insight. So here in this work, we're going to use a continuous time approach. We are trying to create or reverse engineer a continuous time dynamic model represented by a stochastic differential equation. We know that differential equation, ODE, is a dynamic model for deterministic system, right? And stochastic differential equation would be the dynamic equation to represent a dynamic system with noise. Okay, so using stochastic differential equation, we can leverage on some well-established calculus, and then we can obtain very important insights. Now, for example, what are the insights? Using this continuous time approach, we find that the convergence performance of stochastic gradient is given by something like this. So you have two terms in the right-hand side. This is the convergence error. So one term is 1 over s, which decreases with the number of iterations. And the other term is coming from the noise, okay? And this is another convergence error due to the momentum. So this is heavy ball. You see that this term converges very fast, 1 over s squared. But this term coming from the noise accumulation actually diverging. That explains why the heavy ball is actually diverging when you have noise. That also explains why these momentum-based algorithms are very good when you have no noise. Because when you have no noise, you don't have this term, okay? You only see the benefit of this. But when you have noise, then this so-called noise accumulation cannot be ignored. Anyway, so based on this understanding of the reason why this momentum algorithm fails in the stochastic case, we are able to design a better what we call stochastic momentum algorithms. And again, cut the story short. Oops. Cut the story short. We can see that using the proposed algorithm, in the noisy case, we're able to get a superior convergence rate compared to stochastic gradient, but we don't have all this kind of divergent issue of the momentum. So, of course, I skip all the details here, just to show you the possibilities. Now, in the interest of time, I probably won't spend time talking about the other part, but just to highlight, when I say integrated AI with wireless, what I talk about is just one part. When you design communication network, if you have the application, AI application in mind, you can get a much better design in a wireless network. The other half of the story is we can also use AI as a tool to help to solve a lot of challenging communication problems. We can use AI to design a better communication network as a tool. But I won't have time to go over this, but then maybe we can have a next opportunity to elaborate on this. Maybe in the interest of time, let me stop at this point. Okay, thank you very much.